So welcome everyone back, and this event has been a great success as far as I see. It's really good to see many familiar faces. So I will be the coordinator for the next 4 hours. If there is anything, let me know on the chat. It's a great pleasure to have Dhruv Mubayi join us for the next talk. He is a professor at UIC in Chicago, and he will talk on the feasible region of hypergraphs, which is a joint work with his student Xizhi Liu. Yeah, Dhruv, please go ahead.
Great. Thank you very much, Liana, for the introduction. Thanks to Alex and others for organizing this unique event, and thanks to all the people who are coming to the talks. I believe some actually made it to all of them so far. Let's see how long that lasts. Okay, so I'm talking about the feasible region of hypergraphs, and as Liana said, this is joint work with my PhD student, Xizhi Liu. And it's basically a kind of development of a sort of theory or a general picture of essentially many problems in extremal combinatorics. So let's begin with the Kruskal-Katona theorem. And also with the notation that I'll be using throughout this talk. So I'm going to be speaking about R uniform hypergraphs. I'll call them R graphs. That means the sets of edges have size R. And I'm going to be very interested in the shadow. So I've defined the shadow here. The shadow of R graph H is the collection of R-1 sets that lie inside some edge of H, the standard definition. And we're going to be interested in the interplay or the relationship between the size of the shadow and the size of the hypergraph. That means the number of edges. And the classic theorem in this regard is the Kruskal-Katona theorem. And it tells you that if you have a certain size, if the shadow has a certain size, then the number of edges is at most some function of that shadow. More precisely, if the shadow has size z choose r minus 1, where z is a real number, and here we're looking at the falling factorial definition of this binomial for reals, then the number of edges is at most z choose r. Sometimes we see this in contrapositive form. That if you have m edges, then the shadow is at least some number. So if you have z choose r edges, the size of the shadow is at least z choose r minus 1. And equality holds in this case if you have an integer when you can just take all r element sets. And then you have equality for both these parameters. Okay, so this is the most basic, one of the most, maybe the most fundamental theorem in extremal set theory, which relates the shadow size to the edge size. And we're interested in essentially refining this theorem, considering a refined version of this same question, where we don't consider every R uniform hypergraph, but hypergraphs that are forbidding some substructure. So that's what this topic is really about. It's about extending, one way to think of it is extending the Kruskal-Katona theorem to the hypergraph Turan problem. So let me tell you what the hypergraph Turan problem is. This is the classical problem in about hypergraphs, that you have a family of R uniform hypergraphs. We'll call that family F in this talk. We say that a hypergraph is F free if it contains no member of any member of, if it contains no member of F as a subgraph. And here I'm not talking about induced graphs, I'm talking just about subgraphs. And often F is just one hypergraph, but it can be a family. In this talk, we will see examples where it's a family more than when it's a single hypergraph. And the Turan number is the classical parameter, is the maximum number of edges in an F-free hypergraph with n vertices. So the difference, so here the number of vertices is specified, whereas in the Kruskal-Katona theorem, the number of vertices was not specified. But this talk is about combining these two theorems. It's about combining the Turan problem and the Kruskal-Katona theorem. And the structure of the talk is that in the first 10, 12 minutes, I'm going to define the parameter that I'm interested in carefully, state some easy propositions about it, so we understand what we're talking about. Then I'll talk about some very special examples, and then I'll talk about some more advanced things regarding the relationship between these two parameters, the shadow and the edge size. Okay, so here's what I've been alluding to in the last 3 or 4 minutes, which is that we're studying a common generalization. So the main question of this topic is, if I give you an F, and I talk about F-free hypergraphs H, and everything is R uniform, and if you want to simplify matters further, everything is 3 uniform, and the shadow is just a graph. So just think about R equals to 3 for almost everything in this talk. So you have a F-free hypergraph. The question is, what are the possible values of ordered pairs where the X coordinate is the shadow and the Y coordinate is the edge set? Okay, so this is a very, very basic question, and I just want to relate this question to the 2 major theorems of questions in combinatorics, Kruskal-Katona and hypergraph Turan, via these 2 observations. That if F is empty, in other words, there is nothing that's forbidden, and you're just talking about R uniform hypergraphs, then we can already say something about these ordered pairs. Namely, we can say that if the X coordinate is Z choose R minus 1, then the Y coordinate is at most Z choose R. That's the Kruskal-Katona theorem. And something else we can say is that if F is not necessarily empty, well, it can be empty too, but think of F as not being empty, then the maximum number of edges in an F-free hypergraph is the Turan number. So that tells you something about the maximum possible Y coordinate, no matter what the X coordinate is, right? No matter what the shadow is, the Turan problem just says how big is the Y coordinate. So both these theorems are telling you something about the Y coordinate of this set of ordered pairs. And so we're going to try to now take a more detailed look where I kind of tell you something about the X coordinate, and then I ask you the same question about the Y coordinate. Okay, so let's talk about graphs, where this question, not in the exact form that I've stated, but essentially this is one of the major themes in extremal graph theory. Maybe the most fundamental questions in extremal graph theory are precisely about this question that I'm asking in a different form. So let's fix some notation that let's fix T at least 2 and a very large graph. And let's write n of KTG to be the number of cliques of size T in G. And it's convenient in all of this business to think about asymptotics. So I normalize things. So the density is going to be the number of copies of KT divided by the total number of T sets. So that's a number between 0 and 1. And the question that's been studied at length in extremal graph theory is, so what is rho of K2 of G? It's just the proportion of edges. It's the number of edges scaled by n choose 2. So if I give you the edge density, what are the possible values of the clique density? Okay, so if I give you a graph with number of edges 0.25 times n choose 2, how many copies of a clique? Well, the answer is 0, but suppose it was larger than 0.25, like 0.9 times n choose 2. How many copies of K3 are there? How many triangles are there? That's this question. And in fact, this is, as I said, a major question, and it's been studied at length. And this is sometimes called the clique density problem. And this is a picture which depicts what's happening with this very, very famous question. So I'm drawing on the X coordinate. Again, this is not exactly the hypergraph problem that I started with, but it's very, very similar. And actually, it can be phrased as the hypergraph problem if I restrict myself to the hypergraph of triangles that come from a graph and I have no forbidden structure. So then I can put this in the context that I started speaking about, but I'm not going to do that. I just want to give you a feel for this question. So on the X coordinate, I have the edge density. On the Y coordinate, I have the triangle density. We have the Kruskal-Katona theorem, which tells us that the triangle density is at most X to the 3 halves. This is that Z choose 3, Z choose 2 theorem that you saw at the very beginning. And then the question is really, what is the minimum number of triangles? And we know that if the density is less than half, you can have a complete bipartite graph with 0 triangles. Hence, it's 0 until half. And then Turan's theorem or Mantel's theorem tells you that once x is greater than half, you have at least one triangle, which means this lower curve is going above the x-axis. And then there was a sequence of theorems beginning with Goodman's theorem, which is the green curve, x times 2x minus 1, which gave you a lower bound on the number of triangles in a graph with a given number of edges. And then Bolobash interpolated between various points on this green curve to draw straight line segments. And then Fisher proved a better bound, which is actually tight, which is complete partite graphs of unequal part sizes. And then famously, Razborov finished it off by showing that the conjectured extremal constructions for the triangle density problem are in fact shocked by showing these red curves that I've drawn. These are essentially unbalanced complete partite graphs. And then in the last 2 years, there's been a much deeper piece of work by a bunch of authors who I forget, Pikhurko and Liu and Stade and others, long paper where we have much more precise results about what's happening, where we don't even talk about asymptotics, but more precise statements. So this is the clique density theorem. It's the number of triangles related to the number of edges. So this is the t equals to 3 case, and then t equals to 4 was done by Nikiforov, and then the general case of all t was very famously completed by Christian Reicher about 5-6 years ago, I think, maybe a little longer, not sure. Okay, so this is the kind of problem we are interested in today in the hypergraph setting. So it's not a new problem, it's just a sort of twist on a very famous, well-studied problem. So that's what I'm now going to talk about. So I want to basically develop some definitions to talk about the picture that I just showed you in the hypergraph setting. So this is the feasible region. So I just needed 2 or 3 very easy definitions. If I have a hypergraph H, I define its edge density as the proportion of edges. V of H is the number of vertices, R is the size of the edges. So the edge density D of H is the proportion of edges. The shadow density D of the shadow of H is the proportion of the shadow. So I'm normalizing by n choose R minus 1. And then I can talk about, for convenience, it's convenient to talk about just sequences where both these limit exist. So as I said earlier, I'm talking about large objects. So the number of vertices tends to infinity. And instead of taking subsequences and things, it's just easier to restrict my attention to what I call good sequences of hypergraphs, which are just sequences of hypergraphs where the limits of the edge and shadow densities exist. They exist and they are maybe some x comma y. And we say that a sequence realizes the point x comma y if these 2 limits are x and y respectively. So that means anytime I have a good sequence of hypergraphs, I can associate to that sequence a point in the unit square, namely just what is the shadow, what is the edge, how many edges do you have? So if I had a complete graph, then the point in the unit square associated with the sequence of complete R uniform hypergraphs would be the point 1, 1. But I'm never going to really talk so much about complete graphs. Okay, so now I can give the definition of this talk, which is in the title of this talk, namely the feasible region. So if I give you some collection of hypergraphs F, which is forbidden, and F could be the empty set, but it's not going to be. In the case of Kraskov-Katona theorem, it would be, but in general, it's not going to be. Omega of F is the collection of all points in the unit square that can be realized by a good sequence of F-free R graphs. In simple words, a feasible region is basically looking at hypergraphs that are F-free, large hypergraphs, and just asking the very simple question, how many edges do they have and how many edges in the shadow do they have? And then normalizing and taking the limit. So the Turan density is the normalized Turan number. The Turan number is something I defined earlier, the number of edges in an n-vertex graph that doesn't contain F, the maximum number of edges. R is fixed. I'm looking at the chat, but maybe my co-author is here and he'll be answering any questions that you have. If I can look at both places, I'll try to look as well. So the Turan density is the proportion of the edges. And another way to write that in terms of this language is that it's the supremum of the y coordinates over all x coordinates, right? It's just asking what's the maximum number of edges you can have? Well, the maximum proportion of edges you can have. So the Turan density is contained in the feasible region. So in other words, the hypergraph Turan problem is a very special case of the feasible region. It's just asking what's the supremum of this feasible region. So the picture right now is something like what I've drawn, that there's a Turan density, the maximum proportion of edges you can have without F. That's some horizontal dotted line. And below that line is the feasible region. And there are some other things I've written here, which will make more sense in a couple of slides. But actually, this picture at this point is somewhat optimistic because I haven't really told you that the region looks like this. It's just a bunch of points in the unit square. There could be holes. There could be all kinds of funny things happening with this region. And that's what I'm going to discuss next. But at this point, we know for sure that everything is below pi of F, right? That's because there isn't any sequence of hypergraphs where the edge density is more than pi of F, because pi of F is the biggest that can be. So, and in particular, if we knew the feasible region, which is a very difficult thing, we would know the Turan density. So we can't possibly expect to know the feasible region of every hypergraph. Okay, so now I want to make this picture more precise. So I have two relatively easy slides where I try to justify this kind of picture for the feasible region. And that is the projection and boundary. These are very easy things. The projection is just what happens on the x-axis, and the boundary is just basically this, what I'm calling g of f in this red curve. But let's define it carefully. Okay, so the projection is, well, just what it should be, right? You have a collection of points in the 2 dimensions, and you should just project everything to the x coordinate. It's all those x coordinates for which there is some y coordinate. Nothing fancy, just the usual projection. It's possible that there are certain x coordinates for which there is no y coordinate at all. Like maybe you cannot even make an F3 hypergraph whose shadow is a certain size. So that's why the projection is not always everything from 0 to 1. And the boundary is this red curve that I drew above. It's the maximum y, it's a function of x. For every x, it's the maximum y that you have. I mean, technically it's the supremum, but it's a maximum. Okay, so you have a projection, you have a boundary, and there are 3 easy facts. So these are very easy facts. And I just want to go through them just so we get a really good feel for this rather simple object at the moment. The first is that the feasible region is a closed set. So let's prove that by talking. So what does that mean? That means if I have a sequence of points tending to some point, then that point is also part of my feasible region. Okay, so what does it mean that you have a sequence of points? This is a very nice and simple and basic argument. Let's draw a picture. You have a sequence of points tending to this point, and you want to find that this is also in the feasible region. What is a point? A point is a sequence. So you have a sequence of sequences. A point is a sequence of hypergraphs. It's a good sequence of hypergraph that tends to that point in shadow and edge density. So if you have a sequence of points, that means you have a sequence of sequences of hypergraphs. And what you need to come up with is a new sequence of hypergraphs that achieves this final point. And of course, I hope many of you have seen how to get this new sequence of hypergraphs from this sequence of sequences. Namely, you just do a diagonalization argument. Okay, so if you diagonalize, then you get one sequence, and the limit of that sequence is going to be this. And if all the sequences were F3, then this new sequence will also be F3. So, okay, so the boundary, so the feasible region is closed. That was fairly nice and pretty. The second easy fact is that the projection goes from 0 to some point, and then it ceases to exist. Now, what does this mean? This means that it can't happen that this is in the projection, and this is in the projection, and this is not there. That's not possible. And this is very trivial because basically if you have some hypergraph with a certain shadow density, that's the x coordinate, then I should easily be able to reduce the shadow density since I don't care about the edge density. Just keep deleting edges until the shadow goes down. You're never creating a copy of F by deleting edges. So that means that if you started with an F3 sequence, you can come up with any F3 sequence where the shadows are a little bit smaller. So there's no gap in the x coordinate part. That's fact number 2. The only slightly interesting fact is fact number 3, but very important for us. Fact number 3 says that there's no gap in the y coordinate part as well. So that means if you have this point and this point, you should be able to get that point as well. So that's what fact number 3 is saying. There's no gap in the y coordinate. So what does this mean? This means that if you can achieve such a point, then you should be able to achieve every point below that. What does that mean? It means you should be able to come up with hypergraphs or sequences with the same shadow density but smaller edge density. That's a little trickier because you're not allowed to make the shadow any smaller anymore, but you need to make the number of edges go down. So how do you do this? Well, you just delete edges. You just delete edges, making sure you don't make the shadow smaller. And if you think about what will make the shadow smaller, the only thing that will make the shadow smaller is if every r-1 element subset of an edge is not covered by any other edge. And if you reached a stage where this happened all the time, then the number of edges would only be n choose r-1, which is basically 0. So you're never going to get stuck by deleting edges cleverly and making the shadow number of edges smaller, keeping the shadow the same. Okay, so now the picture is getting a little bit better. So the general picture is this. So now this is an honest to goodness picture. There's the Kruskal-Katona theorem, which is at the very top. Oh, that was another fact that I didn't mention, but it should be obvious that that for any hypergraph, the number of edges is at most x to the r over r-1, where x is the shadow density, and this is the edge density. That's precisely the Kruskal-Katona theorem, because even if nothing is forbidden, that is true. So this black curve is always an upper bound for the feasible region. This pi of f is also an upper bound, a y coordinate, and there's some c hat where the projection goes till c hat, and there's some function g, which is the red function. And what I have just shown you on the previous slide says that everything, the shaded part, is all the feasible region. There are no holes in the x direction or in the y direction. This is the feasible region. So that means that studying this feasible region amounts to studying basically this boundary G of F. And there's also a C hat, but the boundary is going to encode the C hat. So the whole business is going to be what's the C hat? What's the G of F? And in plain words, what that means is that if, in simple words, all of this is basically saying, if I give you a hypergraph sequence that's F-free with a certain shadow size, what's the maximum number of edges it can have? That is the only thing that we're addressing. At its core, this is the issue. But before we get there, let's talk a little bit about this G function, because this G function seems to have all the information that we would want. So we want to discuss how pathological or nicely behaved this G function can be. So far, I've been saying nice theorems about this feasible region. It's closed, it's sort of no gaps. There's a nice function on top, but let's see how nice it is. So this is a fairly easy statement. It's the first, I guess, proposition or easy theorem. It says that this G function is left continuous. It has at most countably many jump discontinuities and is almost everywhere differentiable. So it's fairly nicely behaved for any hypergraph family F. So let's see how this works. Why is it left continuous? That means this picture cannot happen the way I've drawn it. And this is very simple, because if you could achieve this point in the feasible region, then there's some hypergraph sequence that achieves this point. Then what you need to show is that you can basically get achieve points that are really close to that point. There's no way it's going to jump all the way down. And the way you make such hypergraph sequences that achieve these little blue points here is you just add isolated vertices to your hypergraph sequence that achieve the blue point, the thick blue point. You see, when you add a few isolated vertices to a hypergraph, what does that do? It keeps it F-free. It makes the edge density a teeny bit smaller, and it makes the shadow density a teeny bit smaller. There's no reason anything should jump by a lot. So this picture will not happen. So that's the proof that this function is left continuous. And there's a little, you can play a little bit with some analysis and conclude that this is almost everywhere differentiable. That's a little more technical, so I won't go into that. Okay, so the point is that this is a reasonably nicely behaved thing. It's left continuous. However, it's not right continuous. So this is already quite interesting, right? It says that there is a family of hypergraphs, D, I'll call it D. This is what I was calling F throughout the talk. So the projection is everything, but at x equals to 2/3, the value is y equals to 2/9. But if you increase x by a little bit, then the value goes down by a substantial amount. And it's a bit too complicated for me to tell you how this works, but for those of you who work in hypergraphs may recognize these two numbers, 2/3 and 2/9. And for those who don't, I've drawn a picture to show you what they are. I mean, the extremal example for this hypergraph Turan problem, whatever it is the complete three-partite, three-uniform hypergraph, which has n cube over 27 edges, 3 equal parts of size about n over 3. And the shadow density is 2/3. That's simple because that's the three-partite Turan graph. And the edge density is 2 over 9, n cube over 27 divided by n choose 3. So that's the example that gives you this red point. So this example is what gives you this red point over here. I haven't told you what's forbidden, but that has to be cleverly chosen so that, and the theorem we need to prove is that if you have a hypergraph whose shadow is even a little bit larger than this, actually even one larger than this, one can prove without even any asymptote, without any asymptotic notation here, then the edge density is way smaller, like it's 2/9 minus 10 to the minus 10 or something. So that's already quite interesting. So it shows that this is not a beautifully behaved boundary function because you can have these discontinuities like this. Okay, so that was, as I said I'll take about 12, 15 minutes to talk about some basic things. So I've done that. I want to now talk about one specific example, and then I'll go back to some more complicated features about this region. So the basic example I want to talk about is the very first problem in hypergraphs, in extremal hypergraphs that was solved. It's a generalization of Mantel's theorem, Turan's theorem for triangles. And it was a problem that was first posed by Katona in the 1960s. And it's phrased in the language of cancellative hypergraphs. So we say that a hypergraph is cancellative if A union B equals A union C implies B equals to C. So in other words, that you can cancel the A. Now, what that means in simple terms is that in the case of a graph, only cancellative graphs are triangle-free graphs. So this was posed as a way of generalizing Turan's theorem in some way to hypergraphs. And the question that Katona asked was the maximum number of edges in a cancellative hypergraph on n vertices. This is n squared over 4. If r equals to 2, it's Turan's theorem. But r equals to 3 is already interesting. So if you think, so we call T3 the family of forbidden hypergraphs in the cancellative situation. And if you think about how you can have this A union B equals A union C, and yet B is not equal to C, there are only two ways that that can happen. And those are drawn in this picture. They are called K43 minus and F5. So if you don't like the word cancellative and this notation, you can just think about this problem as what's the maximum number of triples in a hypergraph on n vertices that does not contain the two triple systems that I've drawn on the right. Okay, that's the Katona's problem for r equals to 3. And this was proved by Bolobash. As I said, this was the very first extremal hypergraph theorem. So in some sense, it's natural for us to try to consider this question in the context of feasible regions, and we will. Bolobash proved that the answer is given by a complete three-partite graph, so the perfect generalization of Turan's theorem. And in fact, one has similar results for 4 and 5, and then this fails to be true for 8 and 9 and larger numbers by some theorem of Shearer. So it's a complicated situation about what happens in general for these kinds of questions. But for r equals to 3, it's well understood. Bolobash proved the exact result. And then Kivash and I, around early 2000, proved a stability theorem, which I'll have to say a little bit about later. So let me start right now. What I mean by stability theorem is we proved that if you have a triple system where the number of edges is quite close to n cube over 27, then the structure of that triple system, if it's cancellative, is quite close to the structure of a complete three-partite hypergraph in terms of edit distance. So we'll get back to this. Okay, so we have an extremal result, the first hypergraph extremal result. And so we decided to study the feasible region. And this is actually the prettiest and most dense slide of this talk, which has about 6 theorems, 6 papers, maybe 100 pages or 150 pages of theorems are in this picture. So let's try to go through everything. So this is asking, what is the feasible region of cancellative triple systems? In simple words, if you have a triple system without those two free-uniform hypergraphs, how big is the shadow? How big is the number of edges? And Bolabash's theorem is that red dot that you see, right? Because Bolabash proved that 2 nines, the dotted horizontal line, is the Turan density. Actually, he did not prove that it happens at x equals to 2/3, but that's essentially what Kivash and I did. So Kivash and I proved in our stability theorem, this yellow area, that if you have close to if you have close to 2 nines, then your structure is close to that structure, which means the shadow is close to 2/3. So Bolabash is the red point. Kivash and I was the yellow thing, and then Liu and I proved essentially the red curve on the left. So we proved that if you have a cancellative triple system with any given shadow, then the maximum number of edges is given by this x to the 3/2 over square root of 6. And what is the construction that achieves that density with the given shadow? It's the construction that I've drawn. It's a complete 3-partite graph with isolated vertices. So the shadow has gone down and the edge density has also gone down. So we proved that that's precisely the G function to the left of 2/3. To the right of 2/3 is a very, very, very complicated situation. So Liu and I proved this up. It's sort of similar to the picture with the triangle density with Goodman and Bolabash and Razbarov. It's a very similar picture that we see here. Liu and I proved this green curve, which is very similar to Goodman's bound for the triangle density problem. Christian Reiher made an observation similar to the observation that Bolabash made to Goodman, to interpolate straight line segments between certain values. I haven't told you what these values are. And in the lower bound, we have some yellow curve, which is some construction, which is a complicated construction. It's an unbalanced blow up of the Fano plane with possibly isolated vertices. So this yellow curve is a construction, and that's what it is. And it depends on what the density is, the size of the blow up and the number of isolated vertices. And then we prove that at certain values, and in particular when k is congruent to 1 or 3 modulo 6 and x is k minus 1 over k, we found the exact answer. And it's basically by the blow up of these Steiner triple systems. So at certain values, we know the answer, and in between, it seems like a very, very complicated problem. I should say one more result that Xizhi Liu proved by himself recently. He proved that around this point, there's like, the picture looks like that. So it's really like a local max, which I'll talk a little bit more about later, because the local max is a weird thing to have in these feasible regions. But anyway, so this I think is a fairly comprehensive understanding. You can view it as a generalization of Turan's theorem on a triangle for triangles, but we do not know the full picture in the right-hand side of this picture, and it seems like it's quite complicated, even though the question is really basic, right? What's the number of triples without having these two hypergraphs? Okay, so that's a special example. I did have another example, which is expansions of Cleese, but I won't talk about that because I want to get to the general theorem. So I'll just say very quickly, there's a more general family of hypergraphs, which I defined a while ago and found their Turan density, because that was the first family where we knew infinitely many Turan densities of different values. And I mean, if you can read really fast, the family is defined, the extremal construction is defined. And so we thought that we should try and study the feasible region of this family, because it's a generalization of Turan's theorem. And yeah, so I had some conjectures. Volec proved this conjecture for some member of this family. It's a generalization again of cliques. And I don't talk about the shadow, but I do want to talk about briefly show you the feasible region, because I will get back to this. So we determined so all you have to know is that there's some family that's a generalization of cliques for hypergraphs. It's called KL+1R, and we managed to completely determine the feasible region. And this is the only hypergraph for which we know the feasible region. So that's something that's nice. And we needed to use some results, generalize some results of Fisher about shadows from the 80s and early 90s to do this. But we couldn't do it for a specific member of that family. So I don't want to say too much, but these are the only two examples where we really know or have a good handle on the feasible region. So it's a tough thing to determine. It's more difficult than the Turan problem, so we expect that it'll be tough. Okay, so I do want to talk for the last maybe 6 minutes or so about some more advanced things about this region. So one is the notion of maxima. So in all these pictures I've been drawing, except for that one picture that I showed you, I've been basically drawing a feasible that goes up and then it goes down. And so the question is that the case or not? And in fact, the answer is no. The answer is that there is a family, finite family of triple systems M, and the feasible region has the property shown in this picture. So the Turan density is 4/9, but there's two different things that achieve this Turan density, two different constructions. This is a very hard thing to do because it wasn't even known that there were any hypergraph problem where you had two different constructions that was proved to be the case. So that's something that's interesting. And I want to say a little bit more about this. So this is related to stability. So one definition that we say that a family is T stable if there are T essentially different near extremal constructions for F, where I don't define anything formally. Essentially different means far from each other in edit distance. Means you cannot get from one construction to another construction just by changing very few edges. This is a phenomenon we do not see in graph theory because of the stability theorem of Erdős and Simonovic. It says that everything is basically stable with respect to the Turan construction, complete partite graphs. But it was a definition I made in the early 2000s because I was thinking about this theorem of Hilton and Milner, which is some theorem in extremal set theory. It doesn't matter what it is. I mean, it's a theorem. It's just about the maximum size of an intersecting family, which is not trivial. In other words, there's no single point such that all edges contain that point. And when r is equal to 3, the answer to this question is 3n minus 8. If you have triples that are intersecting, but no point is in all triples, it's 3n minus 8 triples, but there's two different constructions. I've tried to draw them, if you can take a look at these constructions. And these are essentially different constructions. You can't get from one to the other by changing like, n over 1,000 edges. You need to actually change a positive proportion of edges to change. And so this is sort of explains the definition of T stable. And so the question was back to straight hypergraph Turan problem and Simonovic-Erdős stability. Is there a two-stable family for hypergraphs? And the answer is yes. That's the theorem we proved. This is too complicated to see, but there is some family. It's called M. It's finite. It's made up of three different parts. The first part is just a single hypergraph. The second part has about maybe 10 or 15. I don't know how many. And the third part may be a similar number. So altogether, there are at most, let's say, 100 hypergraphs in this family. I don't know the exact number, but it's finite and not too huge. And the theorem we prove is that the Turan number of this family is achieved by two essentially different constructions. And I show you the constructions over here. The red construction has density about 4/9. It's all triples with 1 point on the left and 2 points on the right. And the blue construction is the blow up of the complement of the picture that you see, and that also has density about 4/9. And the theorem we proved is that the blue construction gives the precise Turan number when n is 0 mod 6. But more interesting is that this is too stable, which means that if you have a hypergraph without a copy of M with density very close to 4/9, it has to be very close to one of these two pictures that I showed you. And in particular, that implies that the feasible region looks like this. So this was a difficult thing to do. And so it suggests that essentially this feasible region can be rather exotic. The nice theorems I started off with in the beginning of this talk are probably the only nice theorems, that you can probably start doing weird things if you work hard. So the first question that you have when you see such a theorem is whether you can have T different things. And this is something that Christian Reicher and Liu and I did, using some of the ideas from the previous result, but more ideas. That for every T at least 2, so T is equal to 100, there's a finite family of triple system, which is 100 stable. So this is a difficult thing because I need 100 different constructions for one thing. I need them to have the same density. I need all of them to not contain this copy of F, and I need to be able to prove all this that they are stable. And proving things in hypergraphs is difficult. So it's not going to be easy, but we managed. And so that shows that this can be quite exotic. And there's a natural question that comes when we have such a theorem, and I'll ask that now because basically that's all I have. That's the last main theorem I have. I'll just end with some open problems. Okay, so here are 4 open problems. There's many more. The first open problem is quite interesting. I think it is a very simple, concrete question. What is the feasible region of the Fano plane? The Fano plane is one of the most well-studied hypergraphs in extremal hypergraphs. We know the Turan number, it's 3/4. We even know it exactly. We know the the extremal construction. It's a complete bipartite triple system. I've drawn it. It was a conjecture of Schoch. Decane and Furedi proved it. It's a short proof, maybe 5 lines. There's several other proofs. It's a very, very well understood object. And so we thought we should be able to figure out its feasible region, but I wrote it in yellow. We have no idea about what happens. All we know is that when x is equal to 1, y is equal to 3/4, right? Because if you look at this construction, the shadow is everything, and the edge density is 3/4. So this construction is this point in the feasible region, but we have no idea. We really have no idea, and we should have an idea because this panel is really not nicely behaved, but we couldn't do anything. So that's an open question. Another question is to extend this theory to not just the shadow, but the 2 shadow and the 3 shadow and the 4 shadow. So instead of the unit square, you could talk about the box. And we didn't think much about this, but perhaps there are some interesting things to be said that are not completely easy generalizations of what we've already done. We don't know. The third problem we thought about a lot, which is to extend the final theorem that I told you about T maxima to the case of infinite maxima. This seems to be true, but we have no way to prove it. So there should be an example of a hypergraph where you have infinitely many extremal examples. There are conjectured examples for such things. The most famous theorem problem in a hypergraph is the K4 conjecture, where there are infinitely many examples. It turns out that the shadow sizes are the same for that. So even if you prove that, you wouldn't get this problem 3. But it suggests that problem 3 it should be true, but we don't know how to do it. And I'll end with just one last question, which is the question of whether there's a local max. We couldn't find such a thing. But again, my philosophy with these things is anytime there's something weird, the answer is probably it can happen, but it's too hard to figure out how to make it happen. But it would be good to prove some basic things. And I think these are some nice places to start. And that's all I have. So thank you for your attention.
Thank you, Dhruv. I invite everyone to unmute themselves and give a round of applause for Do we have time for questions?
Can I have one?
Questions?
Yeah.
Of course.
I have a question about the cancellative 3 graphs, that problem. You have there 2 forbidden subgraphs. One of them is on 4 vertices, right? And it can be easily dropped for the Turan problem. The density will be the same. So does your region change when you have only F5 if you throw away the less important subgraph?
Yes, I think we know the answer, and I don't. Shicha, do you remember the answer to this question?
Yeah, the left part will not change, but the right part, I think it will change.
Yeah. Because we can do some kind of supersaturation for the left part. So the left part will be the same, and the right part we don't know very well. If we just talk about F5.
And I don't know if you looked at the same problem for 4 graphs. I think it should be doable, should be roughly the same as the 3 graphs.
For general R, we know the left part, but the right part is kind of too complicated. We do not know.
And another question about infinite number of maxima. Does it count? Do you know, I think it shouldn't be hard, an example where you have the whole plateau. So you have the whole interval of values of x where you have the same upper bound.
So you mean like this?
A flat top.
Yeah, but that's one of the open questions that we've posed in our paper. We cannot do this. Oh no,
just a second. Yeah. How about if you consider, if the forbidden graph is K5, 3 graph on 5 vertices, I think it should, well, of course, we don't know the answer. Yeah, but if it is true, if it is 3/4, right, then there should be the whole top.
So you would need to find you would need to find constructions of K5 free graphs with shadow smaller and smaller.
Smaller and smaller, not necessarily smaller and smaller, but within some interval.
Yeah, we don't know the answer.
Okay, I think there are constructions like that. You can
some design on 9 vertices, right? There's a construction of yours, I think.
No, not this one. You may have the number of constructions with which give 3/4, right, of all triples. You have such that, say, on one end you have everything except 2 clicks, right? So you have, and on the other hand, you can cover absolutely all pairs. I should look at that.
It's interesting.
Okay.
These are precisely the kinds of questions that we thought about, and many of them were posed at the end of our paper, so you can take a look at that. I can send you a reference.
Okay, great. Thank you very much.
You're welcome.
Any more questions?
Yeah, so Dhruv, you
sorry, Peter, go ahead, and then I'll read
Okay.
Anurag's question in the chat.
Oh, okay. Dhruv, you didn't define feasible region in terms of hypergraphons, which is probably a good choice from the point of view of the talk, but I wondered whether you found them useful in your improving the theorem.
Sorry, I forgot the first, in terms of hypergraph, what?
Hypergraphons.
Oh, yeah, right. Yeah, so we had to make a choice early on how to do this and what language to use, whether to use analytic language or whether to use combinatorial language, and we did what I showed you. And we were using epsilons and deltas in our proofs. So you could phrase, I'm sure you can phrase these arguments in the language of limits without the epsilons and deltas. Yeah. I don't know. I mean, there are some cases, very few theorems I know in this, where phrasing it as in the continuous setting actually lets you do something that you would never have thought of doing in the discrete setting. And related to feasible regions as well, but I don't want to get into that. But this, I don't think is, as I know, is one of those cases. That idea should have been the discrete ideas, I think.
No, that's fine. Thank you for a lovely talk.
Thank you. Dhruv, there is a question from Anurag. I'll read it. It says, would it be interesting to look at the maximum number of edges in a linear Fano-free tree graph for the feasible region? In general, what do the linear hypergraph Ramsey numbers say about the feasible region? I guess he means Turan numbers.
So if you're linear, that means the edge density is always, I don't understand what linear Fano-free means. Linear means the number of edges is at most n choose 2 divided by 3 is a Steiner system. If that's the case, then the y coordinate is always 0. I guess you could, because you're talking about n cube edges, and if it's linear, you have only n squared edges. So maybe that's what you're talking about. Maybe you want to scale the y coordinate according to n squared. Right, so maybe you can do that for certain hyper. You have to be careful though that you can't. If, for example, there are Steiner systems without the Pasch configuration, which is this picture. There exist Steiner triple systems that don't contain this thing. So that means in that case, it's like a complete graph. But you need to pick a forbidden configuration where Steiner systems will have it for sure. And then you could maybe talk about this question where you scale the y coordinate according to n squared. And that maybe is a question that makes sense. But I haven't thought about it. I'm just thinking on the fly.
Okay, thank you very much. Let's thank Dhruv once again for a lovely talk and for answering all our questions.